Hey, hi everyone. Good evening. Hope you are doing well. Thank you for joining me today with hopefully not so heavy stomach. I request everybody's attention, um, especially because of post-lunch session. There would be a little theory part, and then we will go into the hands-on. We will be talking about the most happening programming framework called Apache Spark. But before I start with Apache Spark, I would want to give a little bit brief about what is the architecture that Apache Spark is actually constructed on, why it has been developed in the first place. In order to explain that, I will have to talk about the distributed framework concept. This is nothing but big data solution. Now, we all know we keep speaking about big data. And whenever we talk about big data, the first thing that we need to understand is the definition. The definition of big data is given by V's. There are so many different articles coming up in the internet. Different people have different views, different ways to explaining things. I'm a traditional guy, and I always explain big data using 3 V's. But as I said, there are many V's that can be used for explaining big data. Most of you people are already familiar with this 3 V's. We talk about volume, velocity, and variety. The volume is speaking about the sheer size of the data. The velocity is speaking about the speed at which the data is getting generated. The variety is speaking about the structure or unstructured nature of the data. Of course, we also have semi-structured data as well. Then we have veracity, volume, value, vulnerability, etc. Different V's that are used to define big data. Now, why we are speaking about this big data? Why is it so significant for us to understand, especially because we are talking about trying to construct our careers, right? To build our careers in the space of data world. It could be data engineering, it could be data science, data analyst, probably cloud platforms where you try to understand various machine learning platforms as a service, or various architectures that are used to handle this data. Or in fact, we also speak about MLOps. Any job role which speaks about data has a thing or two to deal with big data scenario. So why this is important? In order to understand this, you need to look at the dynamics of businesses. It all started when we talk about the big data, right? It all started thanks to the computers which allowed data to be digitalized. Prior to this computers revolution also, we had businesses running through, right? And so many different businesses are running. But everything was in offline records. But thanks to the computers, the data is converted to digitalized format. And once it is digitalized, you will be able to store, archive, manage the data, retrieve the information from the data in much convenient way. Right, so that is very important for us to understand on where we have started the businesses from. Now, just look at a small example. Any business, right? Any XYZ business that we speak about, it starts slowly, right? We basically talk about startups, but slowly they become multinational companies, right? They grow to MNCs if they are run in a successful manner, proper manner, which drives the businesses into successes. Then any business that we talk about, any startup, will grow into a multinational company. Now just look at the data that is getting generated in these scenarios. You can clearly say that the data is always proportionately growing. So any business you talk about, any organization you talk about, eventually the data is growing to such an extent that the infrastructure that we have will not be able to support the data that the business is generating. Now, this could be because of broadly put into these three categories. There could be other scenarios also. For example, your infrastructure for any business is generally planned. The right architects team generally brainstorm and they come up with some solution with respect to the infra. So they say that, hey, the business currently is running at this level. The amount of data that the business is generating every minute, probably every day is so much. So projecting or forecasting for probably 5 years down the lane or 10 years down the lane, we need to have the infrastructure developed for some standards. So it is forecasted with respect to the infrastructure demand, and then the infrastructure is set up. Certain benchmarkings will be done. And using these benchmarkings, we forecast and then set up the infrastructure. This is a scenario for any business, assuming normal conditions. But what happens if pandemic strikes? Right? There will be a lot of transformations that happen to the business, these businesses, isn't it? Now, is your infrastructure supporting enough these dynamic requirements? If it is supporting, well, very good. But if it doesn't support, then your business will not succeed. Any organization, right? It will not succeed if your infrastructure does not support, especially because of the technological advancements that we are looking at, where all the businesses run on digital platforms. Right? So we need to look into these dynamic conditions, dynamic challenges that might arise. This is called as scalability. So when the infrastructure is being planned, we are projecting architect teams and basically the infrastructure team which plans. They look into all the various conditions and they do a planning for the scalability requirement in an ideal conditions, but dynamic conditions are going to hamper it. Right? So this is one of the biggest challenge for the organizations, handling big data. The classical example that you can talk about is Zoom.us. We have connected for this session using Zoom as the tool, right? The meeting link is basically the Zoom link. Before the pandemic, Zoom was not so popular. But due to the pandemic conditions, Zoom has seen tremendous growth. This is a classical example. We are doing this session via remote link, by remotely connecting to the sessions. I'm in one part of the world, you people are coming from different parts of the world, you're connecting to this particular session. That is possible thanks to this application, but this application's true power came into the adaptability, right, is when the pandemic situation arises. Now, assume before COVID, probably Zoom was handling 1 TB of data per day. Assume across the globe we are talking about. But after the pandemic, or at the time of pandemic, Zoom was adopted and probably 100 TB would have been generated. Even if you talk about today, it is very easily generating 100 TB of data per day across the globe for various meetings that are getting recorded, a lot of content that is getting generated and all that. It's just a random numbers that I'm giving for example. Okay. Now, is the Zoom's infrastructure as an organization, it needs to maintain the data that is getting generated because of various meetings. So it needs that infrastructure. Now, does the Zoom has this infrastructure which actually supported this sudden rise, sudden popularity, sudden demand? What if Zoom's infrastructure would have not been scalable enough to adapt to these conditions? Right? Can you think of that? We would not have seen Zoom. There would have some other competitor. So to overcome all these scenarios, we needed a solution. And this solution should actually solve 2 major problems or 3 major problems. First major problem is the storage itself. You have 100 terabytes of data per day. Now, where would you store all this data which is getting day on day generated? So much of data is getting generated, right? So where is this entire data going and sitting? Do we have so much of disk storage space? That's the first challenge that we need to address. Then you're processing. So much of data is there and you'll have to process all this data. How are you going to process this, right? So that is another challenge. And dynamically, the data might scale up. So you need to have the scalability also considered. Now, when we talk about scalability, right? Now, you might say that organizations like Google, Microsoft, IBM's, right? These giant companies that we're speaking about, they are heavy pocketed. They have huge money. So these companies do not shy away in investing. But how much would they invest? That is also another challenge, right? You cannot keep increasing the cost. You cannot keep investing in only infrastructure. And even if you are investing, do you have the technology which is supported? Tools, it has to support the processing and storage of the data, especially because your data may be unstructured. Right? You need to have tools support this. So these are the major challenges which needed to be addressed, and to overcome this problem, distributed framework idea was triggered. It all began from Google best practices scenario. Way back in 2004, Google has published a white paper. It talks about how they process the big data. Now, you need to understand that again the plan here. What is the proposed plan? In those days, organizations, we used to have servers, right? Nowadays, we are speaking about cloud. I'll also explain about cloud background also. But when we talk about 2000s, early 2000s, we had servers, data centers and servers, physical servers. So Google used to have a lot of data. If you talk about probably around that time, they kind of used to process 1,000 to 2,000 terabytes of data per day. Okay, in 2000s, that is the amount of data they used to process. So a lot of data was generated, and let us assume for understanding purpose, the logic, we will say that this is server 1. So Google started using the server, and they started loading the data into this, right? And once the server is filled up, they invested in next server, server 2, server 3, so on and so forth. They keep on purchased servers. Okay. Now let us assume we are in 2022, right? So this is server 22. Assume we are in mid of the year, exactly, right? Exactly at the center. 6 months is done. We're in July now. The second half is started. So let's assume that this is half filled. Now, what does Google do? What is their business idea? Google does personalization. It helps in doing personalization strategies. Right? It helps in addressing or developing personalization strategies. What does that mean is it tries to understand individuals based on what they're doing on the internet. So let's say it is you, customer ID 123, okay, standard number 123. As a customer for Google, you started trying to look out for something here. Now, Google needs to understand who you are. So based on your ID, we will be able to understand who you are. But what kind of results it should give you? It does a lot of personalization. Google does a lot of personalizations, right? So when you're trying to look out for something, it needs to be understanding what exactly you want. And that information can be understood when Google can look at what you have done in all the past. So what does it do? It needs to look into each and every server that has data accumulated. So let's say this is 21, server 21. So it looks into this. It looks into this server. It looks into this server. It looks into this server, so on and so forth. From each and every server, it tries to look at the data for this customer ID. It looks out. All these servers are not active. They're basically passive. The active server is this one. Currently, this is where you are working on. But to retrieve the information, it needs to connect to all these servers, which are kind of offline. So retrieve all the information with respect to this customer. Once I have all the data, using that data, we get the information. Right? And using this information, it gives you the result for the various things that the user is trying to do. This idea of trying to retrieve relevant information from all these servers, which contains old data, archived data, this process was published as a white paper in 2004, and they call this process as map and reduce. Map, reduce. So first map the information or the data in all these multiple servers using the customer ID or doing the search. Once you get all this data, you accumulate that data and then try to retrieve the answers or results. Whatever the application that you want to apply. So that component is called as reduce. Retrieving component is called as map. This idea was published in 2004. Later, after 1 year, along with map reduce, there was another solution which was also developed. Two people, Mike Caffarella and Doug Cutting, these two gentlemen, they developed a software which addresses two challenges. This solution that we just discussed, MapReduce, is solving only the processing component. But where do you store the data is another big question. Because whatever we are doing here is basically like storing the data in an offline system. Now, what if, assume a simple question, okay, out of the context, everybody is using laptop or a machine, right? I'll generalize that. I have a machine, right? Likewise, you also have, everybody will have machine. Now, let's say I'm going to declare that, hey, I have a lot of data. I have 2 terabytes of data, which can help you learn a lot of things with respect to data science and right. Let's say Apache Spark. Let's say Apache Spark. Your hardware, your machine is basically, let's say i5, 8 GB memory, and probably 1 TB storage space. Okay, this is your machine's configuration. Now, if I give you a 2 terabyte size data, what will you do? Will you be able to store it in your computer? Simple answer, no, you cannot, because your total disk storage space is only 1 TB. How can you store more than the space that is allowed there? So this was one of the simplest question which was not addressed in MapReduce concept. Because what if I have a data which is not sufficient to be stored in one server? What should we do then? And another point is always one active server will be there. That's all, only one server will be there. And whatever the servers are filled up, they are going to be sent as offline. Right? All right. Now, to solve this particular problem, the 2 gentlemen, Mike Afrilla and Doug Cutting, they said, why not we use a solution to handle this problem also? What does that mean? That means if I have a data which is very big, bigger than the disk space itself, then how do I deal with that condition? Okay, so these were very simple questions that were addressed here. So they said, let us try and build a solution to this problem by constructing a file system which can handle or which can allow us to store larger data when compared to a single node as well. So in this scenario, my storage space will be very, very large. So even if I have 1 TB storage space in my computer, if I use this solution, then I will be able to store the data which is much, much larger than the storage space. Now, what is this idea? What did we do? This solution was called as Hadoop. H-A-D-O-O-P, Hadoop. This is a software, and to understand the software, look at this as an operating system. Hadoop needs to be understood as an operating system. Just like how you have Android operating system, Windows operating system, Mac OS. On the same lines, we have Hadoop operating system. But what is a computer, or what is a device on which this Hadoop is sitting? Right? So what the solution is here, right? The Hadoop, right, is a solution basically saying, try and horizontally increase the capacity of the systems. How do I do that? I combine all the computers that I have into a single cluster. We call it as cluster. Cluster is nothing but a group. So you have many resources, right? This is your high level understanding. But this is your components, right? And here we are saying we have many such components in this particular hardware, the square, that I'm drawing here. The external user, we're looking at this computer, this device. And this device internally contains many computers. Each computer could be of this configuration. But for end user, what do we see here? Combination of all these computers. In order to ensure that all these different computers that are interconnected work without any issues, we need an operating system to control, and that's Hadoop. We call this as distributed framework. The multiple computers are basically distributed, right? Combination of all these distributed computers is cluster. Now, for the external eyes, it looks like this is an 8 TB disk storage machine. Each computer has 1 TB, assume. So we have 8 TB disk storage space in total. 64 GB memory. 8 into 8, 64 GB. Then I have 8 into i5 core, that is literally like 40, right? i40 core. So your regular hardware, when we combined them together to get a supercomputer resources, this is what we see. So your Hadoop software is nothing but an operating system which runs on top of distributed environment. This is the background, friends. And what I'm talking about is Hadoop framework. And Hadoop runs on architecture called master-slave architecture, where we'll have one master and we'll have many slave nodes. We call these computers as nodes. Okay, like this. Master controls the operations that happen in this cluster. And each node that we talk about, each computer that you're seeing here, is having its own respective individual independent machine and its respective operating system. Right? So this is called as Hadoop cluster, in fact. Now for the external users, Hadoop is nothing but a platform, or you can treat it as an operating system, which allows us to deal with this particular computer. Okay. So that's your cluster. But Hadoop solves the problems with respect to big data. And these problems are storage. I now have a lot of storage space, right? Compared to a single machine, when I combine all the machines, I get a lot of storage space. This is nothing but HDFS. This is called as Hadoop distributed file system. FS is nothing but file system. Then we also have the processing capacity, which is nothing but MapReduce. This is no change. This is Google's idea as is. Right? So these are the two things that Hadoop helps us solve, along with the cost issues, because you are talking about open source free software. So you're not investing anything with respect to licensing and all that. And it also is installed on commodity hardware. commodity hardware. So this way also cost is getting saved. You don't need specialized hardware. Another thing is it's a plug and play kind of an architecture. So you can very easily scale up or scale down. Scale up is important. Scale down is as important as scaling up. Especially when you're going for cloud platform, scaling down becomes very important. Whenever you don't require any services, we might want to tone down the infrastructure capacity. Right? Otherwise, it's going to cost us. So scaling up is important, but scaling down is also important. Right? And thanks to its operating system nature, the Hadoop's nature, a lot of organizations were able to come up with their customized softwares which use this infrastructure. The customized softwares are designed in such a way that they allow us to utilize this customized softwares that the companies are developing. All these are basically your data analysis related projects itself. Okay. So if I talk about Hadoop services, we have HDFS and processors. All right. Now, how does a single computer work, friends? This is a CPU, this is, let's say, a monitor, and this is the keyboard, and we'll have probably a mouse. Okay. Yeah. It looks like some robot. Don't really go with my drawings. I'm very bad at it. So this is your local machine, or you can say laptop. You can also imagine a laptop there. Right? Now, how does any task work, or how does your computer work when given a task? If you understand this, then explaining the requirement for Spark becomes easy. Whenever we assign a task to a computer, to process this task, the computer has to initialize a session. When I say initializing of a session, you can imagine it for Python also. Let's say you want to execute some code in Python. So first you launch the software, right? Initialize a session. And for this session, resources are assigned. Two things. What are these resources and how long are they going to use? Those resources are assigned. You need to understand these two questions. A resource is nothing but memory and processors that are required to do the processing. And then we have RAM, processor, and we also have disk storage space if required, wherever it is required. But for processing, we definitely need these two. Right? I mean, this is how a simple computer works, friends. Any task that you do. Now, I want to replicate the logic of how a processing happens in a single computer, right, on this particular cluster. So I'm treating the cluster as a single computer now, and I want to execute various things using this distributed framework. There are many things that you need to understand with respect to Hadoop, of course, before we jump ahead to Spark. But as part of the scope, right, this masterclass is speaking only about Spark, so we'll focus on Spark only. Now, if I have to use this distributed framework as a single computer, then any task that I'm going to assign to this single computer, this cluster, then to execute this, what all things I require? I require processor. Now I have many processors, not one processors, but we have multiple processors. So parallelly we can do the job. At the same time, we can use 2 or 3 or 4 or all these processors to execute certain subtasks. But in order to get all these things done, we need memory, or you can say RAM. But when we speak about Hadoop cluster does not speak about the memory at all. It only talks about processors, and it also talks about the storage space, disk storage. Ultimately, the data is sitting here in HDFS for this Hadoop cluster. HDFS is nothing but a persistent storage location, just like any other folders or drives that we have in our computer. Same way. Okay. So Hadoop has this drawback, which speaks about not utilizing memory. You can see it is only talking about storage component and processing component. But in order to process, what should you do? You cannot use disk storage space, because if you use this, the access of the data by the processor will become slow, weak. It cannot perform at rapid speeds, right? So to solve this problem and try to ensure that it works at a good speed, just like your single computer does when you use memory, the same logic was implemented here, and we look at memory here. But that memory is not from a single computer. It is memory of all the computers which are connected in the network in that particular cluster. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. So we have 12 into 8 GB memory now. Assuming each node here has 8 GB memory, we have 8 GB into 12 as the consolidated memory. Right? 72. Sorry, 96, my bad. 96 GB. Close to 100. Now you have so much of memory, and you'll have multiple processors. So processing becomes automatically very quick when you use Apache Spark. So big data analytics is basically performed using distributed framework. And whenever we speak about distributed framework, there are two things that we need to look at. One is the storage space. The other one is the memory. Disk storage space, that is HDFS, which is given by Hadoop. We can also call it as data lake. Okay, you can use any of the disk storage spaces. But another solution that you require is the memory. Larger the memory, better the performance of a machine. So we are basically taking the combination of multiple systems memory into picture. So this is the architecture of your Apache Spark. This is the agenda. We'll try to understand all these components. Hadoop was developed in 2005. But obviously there will be improvements. because Hadoop had this challenge, it is not utilizing the memory. So development was required, and in 2009, the software was started, right? It was developed. And then it was open sourced in 2010. Yeah, it is open sourced in 2010. Now, once it has become an open source tool, from 2010 onwards, Spark has become the largest open source software communities in the big data entire platforms. Big data works on, right? Big data basically works on the distributed frameworks, right? So we need to look at the usage of the platform. All right. So a lot of people actually have seen this as a very, very solution. I mean, this particular Spark, Apache Spark, compared to Hadoop, because for processing big data, it basically requires a lot of speed, right? Performance is required. Right, and you can see a lot of contributors got in together to enhance this particular product, and it is available in this particular website. You can also look into the contributors as well. Some of the names you can see. So when we speak about the Hadoop architecture, the challenge is that it only uses processor and storage components of the distributed environment. So Apache Spark comes into the picture to utilize memory. Okay, and it is a framework, it's a platform which allows interactive and multi-step analysis to be performed on Hadoop cluster, or generally the cluster. We can also have a single system, of course, single node machine as well. As I explained just now, if you are trying to utilize the map reduce capability that is released by Google's effort, Google's research, then you need to understand that these map reduce tasks access the disk only, HDFS. Because your entire data sits on the disk only, and your processor is trying to access the disk. And for every record we need, we will have to do disk I/O, input-output transactions. So Hadoop takes time in retrieving and storing the data into your disk. And this becomes a repetitive task. So what happens because of the disk IOs, the entire process becomes very slow. So we wanted to utilize the memory, and that's what Spark has. So it is using the concept of memory, that to the memory of multiple computers which are interconnected in the cluster. Right? They are called as distributed memory for your cluster. So Spark uses this memory to keep the data and process the data inside the memory as much as possible. Right? For as long as possible, it is there in the memory. So what happens, because you don't have disk IO, disk read and write operations are not there, the entire task that we are trying to do, where in MapReduce, we are accessing the disk, will reduce drastically because now we are using memory. Right, so that's about the Apache Spark's introduction. So just to give you a quick round of recap, Spark is one second, guys. Spark is a fast, interactive, in-memory cluster computing framework. Interactive means just like Python programming, it uses interpreter as the backend engine. And thanks to this concept, we will be able to run line by line code, and each line at a time. And because disk IO is not there, this read-write operations would not be there for every transaction. Spark automatically becomes fast compared to any of the MapReduce framework related operations. And because it uses memory, that memory is coming from the entire cluster, multiple computers, not from one computer. In the cluster, each computer has memory, isn't it? So we are basically trying to talk about utilizing the memory component of all the machines. And using that, we only do computing. We do not really want to do the storage. So Spark is in fact developed to solve the problem of Hadoop, that is high latency problem. By using the memory concept, Spark executes the data at rapid speeds. So it focuses on speed, at the same time scale as well. And it also has, Spark also has a lot of APIs or you can say connectors, which allow Spark to access data from different data sources. The execution is happening by splitting the task into subtasks, and each of the subtasks is basically given to individual nodes to get solutions. So the compute engine that we are speaking about here is distributed computing engine. And we also say in memory, because entire execution happens in the memory itself. And we say attempt to unification. Attempt to unification basically saying that using a single software, we can achieve multiple things. We are trying to bring in capabilities from other areas also into Apache Spark. And the most exciting thing with respect to Apache Spark for data scientists or data analysts is that Spark comes with inbuilt machine learning capabilities. I'll also show you where we can find all these machine learning algorithms. So it has built-in machine learning capability as well. So this is a brief intro and history and the architecture of Apache Spark. Now we'll take a short break and then we'll come back. So friends, as we have seen, Apache Spark is basically a framework, or you can say a platform, which allows you to do computing using the memory of individual nodes which are connected in the cluster. And the coding, the computing that we are talking about, the processing of the data that we will be doing, will be in an interactive mode. And because memory is being used for computing, the entire application becomes fast. So whenever we speak about Spark, then the first thing that you need to see is that Spark is 100 times faster compared to any of the tools that you talk about which run on MapReduce, the MapReduce framework that we speak about. So Spark is said to have 10 times speeds when it is reading the data from disk. See, ultimately, the data will always be there on the disk itself. Right? When we talk about data, the data is always lying on the disk. When you want to process this data, the required data gets into the memory. And your processor will not connect with disk, it will connect with memory to do the processing. And the results are also to be stored here itself. So when this process is there and when your data is here, the Spark is said to be 10 times faster to any of the MapReduce application. But once the first time when we're accessing the data, right, it is going into the memory first time when you're accessing. And if it is a repetitive task, then it becomes faster. But for the first time, because it is not processing the data directly from disk, rather it is only substituting the values, right? Passing the values from disk to memory. Because of this step, it is said to be 100 times faster. Sorry, 10 times faster. Because disk I/O happens, we need to deal with the disk. But once the data is in memory, then the processing here happens 100 times faster. That's the second part. Spark is a thread-based application. It is used, it is developed using Scala, which is known as a hybrid programming language. It contains both object-oriented programming style and functional programming style as well. Hence, it's called as a hybrid. And using Scala, the Spark application has been developed. Now, Scala is like Java. When you compile your Scala code, it gives you Java bytecodes only, Java class only. Okay, so for processing, we require JVM. And Spark uses a single JVM for doing the task. It's nothing but Java virtual machine. Now this becomes your executor of any task. But each of this executor can handle multiple threads. And under this thread, we have multiple tasks. So you can see a lot of parallelism that can be achieved. Okay, the execution can again become very fast because of the parallel approach. But the challenge is why we need to even look into some tool which is right, like learning extra additional things when you already have Hadoop related ecosystems. So Hadoop, as I said, is like a platform. You can say Hadoop is like your Android operating system. And on that platform, you will have Play Store, Marketplace, where you can download a lot of different softwares, mobile applications. Each application is like a software which is developed by a group of people or an organization or an individual. Right, someone or some company has developed the application. So when you already have Hadoop, why do we need to look into the ecosystem tools? When you already have Android, which is an operating system, why do you need so many mobile applications? Isn't it? So that is the kind of comparison we need to do here. The biggest challenge with Hadoop is the time it takes to process the data. Right? Because everything is on the disk itself. Right? So that's about your Hadoop ecosystem. This Hadoop ecosystem basically contains many such applications which run on top of Hadoop operating system. The beauty is the Hadoop ecosystem tools will always run on map reduced framework, which is basically taking a lot of time. Whether it is directly HDFS commands or whether it is Hadoop ecosystem tools, you have the same problem. This problem is solved by Spark because Spark does not access any disk. Right? Spark would obviously access disk, but only for the first time. But from there on, the entire processing happens in the memory itself. Right? So this is one of the reasons why Spark is more popular than any of the Hadoop ecosystem tools that we have. High latency in Hadoop ecosystem tools. Right? This is the reason for why Spark. This is a small background. Now coming to the features, you can see all these are the features of Apache Spark. It is open source. It's a free software. It is open source. That means anyone can contribute into developing the Apache Spark. It allows you to distribute and at the same time parallelly work together. Right? That is distributed and parallel computations. And it also does not deal with disk storage space. It deals with memory. So the computation should happen in the memory itself. Now, using Apache Spark, you can develop interactive applications or iterative applications. Spark is definitely built for handling iterative tasks, repetitive tasks. And because we are talking about cluster here, we always need to understand that the data is also distributed. Because of the cluster nature, we might have to distribute our data. So we'll have distributed data sets. Batch and real-time applications. Hadoop does not support real-time applications. Hadoop only supports batch mode applications. That is, your MapReduce does not support real-time. The beauty of Spark is it's a platform. Now, on that platform, if you want to develop some code, you can either use Python, Java, Scala, or R programming. Along with that, you can also do SQL, Spark SQL. But these are the four, I should say, programming interfaces or programming languages, right, which are supported by Spark. We do not need any specialized hardware, right? It's very simple. You say commodity hardware is good enough. Right? And Spark also has fault tolerance capability. So any task that is getting crashed out or failed, then Spark handles that failed job. Now that the failing of the job can happen because of various reasons. right? If it is because of the hardware, then fault tolerance is anyways part of your Spark's capability. Scalability. Now we're talking about Hadoop cluster, and Hadoop has plug-in architecture, right? Plug and play architecture kind of service. So the same capability is also available in Spark. And especially, as I said, scaling up and scaling down, both are important, not just looking at scaling up. And the Spark is also OS independent. It either works on Windows or Linux. Right? We can very well install them and work. Of course, Linux is where we need to specifically look at, because servers and all that we speak about are hosted using Linux operating system. These are bunch of the features with respect to Apache Spark. Now let us try and understand what does unified engine means. When big data started way back in 2004, 2005, it basically revolutionized on how big data can be processed. Prior to that concept, we did not even have a big data solution. Okay. So 2004, 2005, in fact, when Hadoop was released, it was welcoming, right, software. And people started using it, and probably till early 2010s, the Hadoop architecture was very popular. But in order to work with Hadoop, we needed to have the applications installed. Now, when I say applications, there are n number of different applications that are developed on Hadoop ecosystem. And each of this application was specifically developed to do certain tasks. For example, because data scientists, right, you understand machine learning. So Mahout is one such example where the software is used, right? This particular software is used to implement machine learning capabilities on big data, which is hosted on Hadoop architecture. Okay, so that is one of the softwares. We have Impala, Giraffe, Daze, Drill, Hive, Pig. Hive, Pig, these are more popular. Hive and Pig specifically. These are the two programming languages or tools which are very popularly used in Hadoop framework. One is a data warehousing tool, one is a ETL tool. So the problem here is a single software or a platform that we have here. Hadoop is the platform. In order to use Hadoop's platform, we have to learn different tools. It's like you're using Android phone. For getting various things done, you'll keep installing your mobile applications, right? Different mobile applications. So many mobile applications are readily available, isn't it? Billions, in fact. Recently, Google has come up saying that there are more than 1.6, I think, billion. I'm not sure about the number, but they have mentioned that in billions, right? Mobile applications which had to be removed. Why? Because there is no transactions happening using that mobile application. Generally, people try to just develop the applications using Android operating system. It might not go into the production, or it might be a something which is developed by a single user for learning purpose and all that. So like this, there are so many mobile application, it seems. So Google has stated that they are going to remove them, and if anybody wants to have them in the right Google Store, then they have to reload it. This has recently come up. So if you have any such applications, just keep checking for the updates. So the problem here is, from a data processing perspective, how many softwares will you learn? Yeah, think about it. So many different mobile applications. Same way, you have so many different applications on Hadoop's ecosystem as well. Now, as an individual, you cannot master all these different applications which are available. So you need to either get yourself trained on these tools or hire someone who's already expert. Now, from an organization perspective, both are not productive. Right? It's not appropriate to use because the learning curve will increase if you're using the existing resource to get trained on these applications. And if you want to hire some expert, then the problem is that you cannot hire so many different people who are familiar with different tools. So as I said, both are not practical. This is where Spark comes into the picture. It's called as generalized unified engine or general unified engine. It's generalized engine. That basically means you learn Apache Spark only. That's all. You don't need to learn all these different variations, varied applications, because Spark alone can help us solve all the different business problems that these multiple tools are doing. A single software can do all those things. That's the logic of Apache Spark, and it runs on generalized computing framework, whereas Hadoop uses, the MapReduce uses map and reduce framework, map jobs and reduce jobs framework. So if I have to compare Hadoop with Spark, as you can see, if I have to compare with Hadoop and Spark, you will see that the components of Hadoop, right? These are the components. The yarn is the cluster manager, because we have so many resources involved, right? So we need some resource which can manage the services. So we have cluster manager in yarn. Then the storage component. This is right, the same platform on both the sides. But if you talk about the computing framework, Hadoop has MapReduce, where Spark is doing the computations. This is basically developed for doing the computations itself. Now, Hive is one such software which is developed by Facebook. It's a data warehousing tool. On big data. So what all things your data warehousing does, it's nothing but SQL on Hadoop, okay? Also known as HQL, Hive Query Language. This is done by Spark as well. We have a module called Spark SQL. Mahout, just now I explained, it is nothing but machine learning library. We have same Spark machine learning in Spark. Then Strong is to ingest the live data. Spark Streaming does that for us. Like this, we have different tools which are basically developed on Hadoop. All of those are handled by Spark. But Spark requires storage. Hence, it is relying on Hadoop's HDFS as one of the sources. It is not the only source, but that is also a data source. Now, if I compare Apache Spark on Hadoop, then you can see here, Spark is only compute, whereas this is storage and compute. It works with MapReduce framework, map jobs and reduce jobs, whereas this one is a generalized application. You don't need to deal with the partitions directly here. Map jobs is like dealing with the partitions. Right? That is not required here. It is more like a generalized computing. Hadoop always works with the data which is there on the HDFS only. There is no other option. It only deals with storage device. Whereas Spark can have the data stored in memory. And Hadoop is not defined or not developed for iterative work, whereas Spark was developed to do that. It's right, one of the key, you can say, feature. It does iterative works very, very quickly because the data is already there in the memory. Hadoop does batch processing, whereas Spark does generalized processing, and it can also do real-time processing with these kind of speeds. And language flexibility is something that we have discussed. These are some of the benchmarking numbers. When Hadoop was released, Hadoop was giving us world record. It's a world record in processing 100 terabytes, because prior to that, there's no solution which could process 100 terabytes simply, right? Easily. So Hadoop used 72 minutes to process this data, and this is world record. But this world record was like completely broken down when Spark was introduced, and Spark processed the 100 TB just in 23 minutes. 72 minutes compared to 23 minutes. And another important thing, nodes. The number of nodes is 2,100 in Hadoop's case, whereas 206 in the Spark scenario. So what does this nodes means? A node is nothing but a computer in the cluster. So in order to deal with Hadoop for this 100 terabytes of data, 2,100 nodes were used. Spark has 10 times less. Right? Spark is basically processed on data which is 10 times less. 206 servers only. And the time it has processed is 23 minutes. Very, very short time, I would say. Right? So this is the benchmarking with respect to Hadoop. This is what is the flow in Hadoop MapReduce framework. Data is always there on the cluster's disk storage space. Individually, you have many computers interconnected, but for this cluster, there is one virtually created HDFS. This is like your storage device. So data will be there here in the Hadoop HDFS. So disk IO is happening. Read-write operations. We start with map tasks, retrieve jobs. Now to retrieve the data, we obviously have to do read-write operations. Now, whatever the data that are accumulated, that are collected by different servers in the cluster, right? The result that we get, the key and value pair, key and value pair intermediate data that comes up. I'm calling it as intermediate data because this is temporary. Because this is not what we want, but unless until this intermediate data is available, you cannot do the actual processing. So the map jobs give the output, which is always in key and value pair architecture or key and value pair style. Now, once the data is accumulated here, the key and value pair intermediate data, you basically store that, right? Intermediate data on the disk again. So here I'll have IO and the data comes and sits in the disk. Disk I and O. Input and output operations. Once the intermediate data is coming here, then reduce task. Right? So we use reduce task here. The input that we have obtained, passed to the map functions is the raw data. This is nothing but raw data. The output of the map jobs are basically the intermediate data, which will be in key and value pair structure always. It's like a structured data. And this intermediate data gets stored on the disk, and we are reading that disk again. Right? The disk is basically stored here again. Now, once this input, once the output that I have assigned are obtained from map jobs, this data, that input intermediate data that we're talking about, becomes output here for the map jobs. And that output, we get output as the intermediate data. That output is passed as input here. Okay, this data is passed as input to the reduce functions. Once we get the input data, the reduce function does the actual task and gives us the result. That result again has to be stored on the disk itself. So this is your source. So how many disk read-write operations are happening? 1, 2, 3, and 4. So disk is being accessed at every stage. So total operations are 4. Now what does Spark does? How is it different? When the data is being referred to or being accessed, right, for the first time, ultimately data is there on the disk itself. The raw data that we talk about is on disk itself. That disk is your HDFS storage space. Whatever the data that we want to process, it goes into the memory. And the Spark does the task on the data which is there in the memory itself. This becomes input and we get result. This becomes your output. The output that we are receiving is stored in memory only. And this data becomes input for your Spark application. Let's say this is first Spark application, this is second Spark application, and whatever the results that we are getting. These results can be stored onto the disk, or if you want to showcase the results on the console itself, then we can do that also. So the second disk read and write operations are optionally. This is optional because you can directly show the result or store. So here the disk operations we see is only happening once for mandatory. This is disk read-write operations. Everything else is there in the memory itself. The processing, you talk about the right data, the intermediate results, all those things are sitting in the memory itself. So compared to 4 times you're referring to hard disk, just referring once, right, is the best option. So this is how your Spark works, and it reaches that speed because of this flow itself. And this is how your Spark sits on top of Hadoop cluster. The Spark is also a distributed environment. So you'll have master and slave architecture here. Right? So the master is called as driver program. The slaves that we are looking at are called as worker nodes. Okay, so we have Spark, master and slave architecture. The worker node, worker task is, or worker component, which is the slave component, is working on data node in the Hadoop cluster. The name node is considered to be the master. So you can imagine that on name node, we will have the Spark driver service also installed and running. So this is the architecture that Hadoop uses on your, or Spark uses on your Hadoop. And this is the flow. This is what actually happens. The driver program, which is the Spark's master, is looking into the application. This is your master. And this master communicates with the cluster manager. Spark also has an inbuilt cluster manager, which can manage the cluster. Right? And this basically is requiring the information that is coming from the slave nodes. And using cluster manager, if I talk about Hadoop, it is Yarn. Right? Using this cluster manager, we will try and assign the tasks to the respective nodes which are freely available at a given point of time. And on the worker node, you can see you have an executor. This is nothing but JVM. And these things are getting executed by the task. So we have tasks, we have multiple tasks which can be run on a single worker node. So this is the architecture, and this is how the data moves. This is your master. After receiving the master, analyzing the requirement, it breaks down the task to subtasks and it assigns the data, and then it is retrieving the results on that particular data. And once all the subtasks complete, they pass the information back to the master, where master is consuming the data for probably different types of decision making. And this is the architecture that you need to refer to, or you can say this is default architecture that Spark has. If you look at this unified, this particular tech stack, you have 3 different layers. One is the end user layer or programming interface you can talk about. The bottommost layer is talking about the source. This talks about the data. And these are the capabilities of Spark, which analyzes the data. And as we discussed, Spark is only a computing framework. It does not have storage component, so it cannot store the data. So it also has this workaround. That workaround is nothing but the readily available APIs, which allows us to communicate with various different data sources. Some of the examples are given, which are standard. Hadoop, Cassandra, Hive, HBase, Postgres, CSV, that is flat files, JSON files, Agro files, Spark files, SQL databases, then Elasticsearch instances as well. In short, we will be able to access any source. Now, once we have accessed the data, the architecture, right? The architecture is designed in such a way that Spark does not work on the data which is there on the disk. Spark works on the data which is in the memory. So whatever the data that we are connecting here, the source that we are connecting here, the data that is getting ingested from these sources will directly go into the memory, and we call that object which is stored in memory as RDD. Okay, that is the default data abstraction in Python, RDD. But thanks to the advancements of Spark, I think Spark 2.7 or 2.8, latest right, changes have been occurring, where you can see data sets are also supported now, not just RDD, which is unstructured data. It also allows us to deal with the semi-structured and structured data also in a data frame format. Data frame is nothing but an API which allows the data to be converted to a proper structured data. Okay, and on top of that, we have Spark Streaming, Spark SQL, machine learning, and graphics. These are the 4 different capabilities that Spark has experimented on, or you can say libraries. But Spark Core is something which is more generic. Now let us try and understand each of these components. We'll start with Spark Core. Spark Core is the most important component. You can say it is like the fundamental component. And it contains all the required basic functionalities that that can be used for processing. It generally handles the task of you can say fault recovery, ensuring that the storage systems are properly accessed, scheduling is done properly, the memory that we speak about that is managed appropriately, right? So all these things will come into the picture which Spark Core handles. Then Spark Core is a component where the API is placed, which converts the data that is coming from an external source into a Spark's memory object, which is nothing but RDD. So it's like the projection of the data. Right? Whatever the data that we have in the Hadoop cluster distributed environment, we will try and take those pieces which are distributed across different servers into a single instance in the memory. Okay, Spark Core is basically the API which is giving us the RDDs. The full form of RDD is resilient distributed data set. And it is unstructured, by the way. Remember that point when we, after a few slides, we'll talk about RDDs specifically. You'll understand. The Spark SQL is another very important component and very heavily used component after Spark Core. In fact, more than Spark Core, I should say, is basically a querying tool. SQL is the most or is the oldest data processing language. SQL, which is also known as structured query language. Right. So similarly, we also have a Hive, which is developed by Facebook, which tries to replicate SQL only. Okay, so both these capabilities are combined together, and we now call it as Spark SQL. So if you have a very large data, then querying on that large data becomes a little time-consuming task. Whereas Spark SQL does the same job at rapid speeds. So if you wanted to deal with structured data on big data platforms, then Spark SQL is something that we will have to use. Then Spark Streaming. Any live data that is getting generated, we can process that. We're not talking about storing, remember? We can process the live data that is getting generated using Spark Streaming. An ideal use case is, you can say, Apache Kafka, which is a data ingestion messaging system, which is used for data ingestion, is used to ingest the real-time data that is getting generated. And then on that data, as and how it is getting generated, we can design an application which can process that particular data for a specific reason. And that can be done using Spark Streaming. Then we have machine learning library. This is deprecated now. RDD-based machine learning library models are deprecated. But this is nothing but your machine learning capabilities. We have ML, Spark ML is something that we are basically using right now. It's nothing but data frame based and RDD based approach. RDD based approach is something which is deprecated. Newer version will not have that. Then we have graphics. This is the library which is used to analyze the graphs. Right, like your social media network, where people are interconnected, like aeroplanes, which are where aeroplanes are connected from one terminal to another terminal, one airport to another airport. Right, so graphics is a module which allows us to analyze the network. This is the interactive medium. It's called as Shell. But this, remember, Shell is available only for the Python and Scala. We still have other components also. Other programming languages, like it supports R programming language, it supports Java, it also supports SQL. Right? If you are trying to write a program on Spark platform using Java, then you can take any notepad and start developing your code. If you're using Scala, then you'll say Scala shell, right? Or you can say Spark space shell, and you'll get this session. For Python, we use Pyspark, and that is what we are going to learn. All right. We have discussed about the architecture of Apache Spark, the features of Apache Spark. We have also understand that it is master-slave architecture, where master is called as Spark driver, slave is called as worker node. Right, and we have also seen the tech stack, which is also known as unified tech stack of Apache Spark. And we have seen the components of Spark core. Then we have RDDs in the logic. Then we have various components like graphics, machine learning library, right? These services. But in order to implement those services, we need to look at the building blocks, the most important aspects of your Apache Spark. If you have these three entities, building blocks, then we will be able to use Apache Spark. So what are these things? We'll talk about that. We'll again go for a short break. We'll return and then talk about this, and then we will do hands-on. We'll start with hands-on. So Apache Spark is nothing but a platform, right? Or a software, sorry. It's a software which helps us process the code that you are trying to develop using the capacity of all these multiple computers. So Spark allows you to use the full capacity of all the computers which are interconnected. Now, if you are doing Python for, let's say, machine learning or some code you're writing, then you're going to do the same thing. Rather than on one node, you will be doing on cluster. That's all. But in order to utilize this cluster, Spark looks at these three components or three building blocks, we can see. The first one is the Spark context. This is nothing but the environment, right? The infrastructure, you can say. And then we have data. This could be RDDs by default, but it can also have data frames or data sets. And what type of operations you are trying to do. Broadly, they are classified as transformations and actions. Now, let's say I have this Hadoop, this cluster. I'm not talking about Hadoop alone. I'm basically generalizing it, and I have a cluster. In my cluster, let's say I have 9 computers which are interconnected. Okay, 9 computers are interconnected. This is your cluster. Now, each computer, let's say, is having 8 GB memory. So this basically gives me 72 GB. Each computer, let's say, has 1 TB storage space. So this gives me 9 terabytes of storage. Each computer is a very basic i5 computer, i5 core. I'm not even talking about i7, okay, a regular thing, i5. So that means I have, you can mathematically, you can say i45, right? This is the capacity which can be basically obtained. Though we do not do this calculation, but for a comparison perspective, I'm doing simple mathematical calculation. Now, if you want to perform a task, what would you do? On a single computer, remember I talked about this. If I have a single computer, then on the single computer, the resources are assigned for a task. These resources are pulled from the complete set of resources that is available for your computer, because you're not only doing this task, there will be multiple tasks. So not the entire set of resources are assigned for this task. There will be other tasks also. Whatever the resources are that are required, only those resources are assigned. Same way here. Do I require all these resources to process this task? Maybe not required. But you can customize it. You can basically define what resources are required. We don't talk about storage for processing here, so you really don't specify this. But how many CPUs or what processing capability you want? I will say, I need 2 CPUs to accomplish this task. This is a very simple task. Then the memory. You're going to say that you need probably 10 GB memory to solve this problem. Not more than that. Maybe you'll say 20 GB, right? Let us increase that, 20 GB. So from 72 GB memory that is projected here, this is your RAM. For an end user, it looks like a 72 GB memory stream. But the 72 GB is coming from individual nodes. Similarly, 9 TB is something that you will see. This is your HDFS, right? 9 TB. And then you have processors, right? So when you talk about this task to be executed, we are trying to consume the resources which are required. These resources are defined here. You're defining. So to accomplish this task, you are saying take the set of resources from this pool. This is your Spark context. It's like your environment that is used for processing this task. Spark context. Similarly, you can create multiple Spark contexts to work on different tasks. Execution environment. Now, Spark works on cluster. Spark works on a local machine as well. Okay, it is generalized, right? So it can be worked on, it can be used to work on the Hadoop cluster, or it can also be working on your standalone computer. I will show you the installation of Spark on your local machine. It's a very simple steps. We'll do that. And once this environment is described or initialized, we need to initialize. Then we will start doing the execution. But to do the execution, we need data. Now, this data for Spark has to sit in memory, right? It's not on the physical storage devices. It is in the memory, and this memory is coming from a distributed memory concept, because each computer has only 8 GB. But for the task, I need how much? 20 GB. So that means maybe I'm taking these two, 16, and partially some of the memory from this. So 20 GB I'm taking. Let's say this portion is 20 GB. Within this 20 GB, we will have the data. Spark works on the object which is there in the memory. That is called as RD. It's a memory object, right? So it is only read-only concept. The data will only be read-only option. It cannot be altered, of course, because it's a projected. So the actual data could be here or here or here or here. We don't know. But we project that particular data into the memory. Now, on that memory object, the operations are executed. So these are the 3 building blocks for Apache Spark. You understood what is Spark context. Now the Spark context has to be initialized. It is the execution environment, you can say. And without this, there is no Spark application execution at all. And to start Spark context, we can use these functions. You can initialize the Spark context using the commands in the Spark shell, or you can write a code, and within the code, you can initialize your Spark context. Or when you're executing a command, we use the Spark submit command, which initializes the Spark execution environment. In that Spark submit also, while you're doing that as an argument, you can do the Spark context definition and execute. So these are the 3 options that we have. Now, Spark context can be executed on a local machine. That means a single node. Star refers to the number of threads. K is also the worker threads that we speak about. If you don't mention anything, then it is one single worker thread that is used for processing. That is sequential processing happens. If you know how many threads you want, you pass that as an integer, as a number. Then star symbol is when you don't know how many logical threads are possible on your hardware, you basically say that you want to use everything, right? All the possible threads. So then you just put star there. But if you want to use the capability of a clustered environment, then you will be using the cluster managers as your masters. So if you're running on Hadoop, you'll have Yarn. This is another cluster manager for Hadoop. So we will be using Yarn as the master. By default, Spark has cluster manager, which can be accessed on 7077 port number. Similarly, for different clusters, we have different cluster managers. We can use those cluster managers. For Hadoop, the cluster manager is called as Yarn. Yarn will decide how many resources have to be assigned to your application if you are using the cluster manager as your Spark context master. So that is about your Spark context. Now, RDD, as we discussed, is the data projection in the memory. It's called as resilient distributed data sets. Resilient means the ability to recompute. That means it's memory object, right? It is not the physical data. It's a memory projection. So there's nothing like the data is getting deleted or data is not available kind of a scenario. Data is a read-only option that you get. So even in case if the data is missing, some right component is missing in the data or some records are missing, because it's a memory projection of the physical file, we will be able to reproject. So there's nothing like your data gets lost. Okay, the RDDs gets lost, not the data, but RDD cannot be lost. If your original source file is lost from the disk, then RDD cannot be created. And this data is distributed because physically in Hadoop, the data is actually getting stored in multiple systems. These are all multiple systems. Each system has 1 TB. Let's say if I have 2 TB disk file, then obviously I cannot store a 1 TB disk, right? 2 TB file on a 1 TB disk. So what I do is I'll split this. This is one of the features with respect to Hadoop. It internally partitions the data, stores the data by splitting it into different nodes. That means your data is getting distributed and stored. When you want to work on this data, the projection of all these distributed pieces happen here and you'll get single strip. This is your data, which physically is actually located in different nodes. So Spark is working on the distributed data as well. This is basically how Hadoop deals with your data. Next. The logic of RDD that you are looking at, right, is nothing but memory abstraction. As I mentioned, it's like a projection. Your original data is here. Let's say in this node, in this node, in this node, and in this node. Physically, the data is split. But when you want to try and work with this data, probably this is stored into the memory of the individual system. And when we talk about Spark context, we are trying to store or access this particular memory locations. This becomes your RDD. I mean, this is your Spark context memory. Within this, we will have RDD. Whatever the records we have, we are projecting in this particular space. So it's the memory projection, you can say. Whatever the transactions that we are doing using Apache Spark happen here in the memory itself. We don't go to the disk. Okay. So that is the logic that we have in the Spark. Now, if you actually want to work on, let's say, a CSV file, I'm assuming everybody is a data scientist, at least we are learning data science. So if I have a CSV file, what we do in Python, we say pandas dot read underscore CSV. What does this function do? It takes the content of this file and puts that into the memory. And we basically call this as sessions memory. The same logic is happening in the Spark also. But Spark does not deal with one node, but it has many nodes. But the functionality is same. The logic is same. This is my cluster. This is one node. It has its own memory. Another node, it has its own memory. Just like hard disk, where we talk about HDFS. This is nothing but the capacity of individual nodes combined together. Same way memory. This is memory combined here, here combined. Each node has 8 GB. And we are saying, combining all this, we have 48 GB, 6 into 8. So 48 GB memory is available here. Now, when you want to work with the data, when you're saying load the data, you are defining that, hey, this is my Spark context. The Spark context is nothing but a memory string. Each computer has 8 GB. You're saying 12 GB is what you need. Assume this is Spark context where you're saying 12 GB memory is assigned for Spark context here. I don't need more memory. I just need 12 GB. That's good enough. So when you say read.csv, what happens? Whatever the file you have is getting loaded into this memory strip. And this becomes an RDD because you're dealing with the data which is there in the memory, not on the physical file anymore. Okay, so that's the logic. And how does this file get stored? By splitting it into different nodes is Hadoop's logic. That has nothing to do with Spark. This data ultimately is getting projected into memory. Once it gets projected into the memory, the Spark action comes into the picture. There is nothing like buffering. You are already using the memory. There is nothing like memory. You are already loaded. You want to watch a movie on OTT platforms. You either stream the movie or directly download the movie and then watch it. When you say downloading, it is getting basically placed at some location. That location is nothing but memory. In my RAM, I'm storing this particular data. There's no buffering question here. So this is basically the logic. Your entire data is getting projected into the memory. That's where your RDD is created in the memory. And once it is created, we start doing the processing on this memory. So that's your RDD's logic. This allows in-memory computations. These are the properties of RDDs. Spark only used to understand RDDs alone. Like SQL programming language, when we talk about SQL programming language, it only understands tables, rows and columns. Same way, if I have to use Spark, then it used to allow only RDDs, memory projections. But these memory projections are unstructured. Whatever the content that we have, you just dump that into the memory and then process it. Okay, so primary data abstraction or data format, you can see. This is the unique entity. And for every RDD, you have a ID also generated. We'll see that. I'll show you the ID also. And this is in memory. Right? So RDD is stored in memory. And because it is memory object, you cannot alter the actual data. So your data becomes read only. You can create a new RDD if you want to make any changes, but that is not getting affected in the physical store. So it is immutable. Immutable is nothing but you cannot change. Once RDD is created, you can do manipulations and then you can probably recreate a new RDD, but the existing RDD will not get changed. And these operations are also known as lazy evaluated operations. So when we go to the next topic, that is operations, there are transformations and actions. We will discuss about lazy evaluations under that operations. This is nothing but transformations. Transformation operations are nothing but lazy operations. The data can be cached. Cached is basically nothing but you can keep this data as long as you wish on your memory. And because you have read-only object, which can be further partitioned, split into subsections, and each of the subsection can be further processed by the processors which we have in the cluster. So parallelly, all these partitions can be executed. So parallel processing is also available. Data, as we discussed, it's already partitioned. It is physically partitioned thanks to Hadoop's concept. And for Spark, because the data is in memory, we can logically also split the records or data. Though parallel processing is allowed, within each partition, the data will always be accessed and executed sequentially only. Right? And because memory object, Spark has fault tolerance and data locality capabilities. Data locality means it's basically trying to create the RDD by understanding the physical location of the system, the data in the system. Then we have scalability. If you need more memory, you just keep adding these servers and you'll get processors and memory. Spark only deals with memory and processors. Okay, it does not deal with the storage. But one thing you need to remember is that once you have created an RDD, it is local to a Spark context, right? Memory abstractions. You cannot change memory, which is logically partitioned to another partition, another Spark context. So what I'm saying is, if this is your memory, this is your cluster, we are saying, hey, this portion I'm creating as Spark context. Let's say SC, we are giving a name SC1. Now, if you are creating SC2, then the environment uses memory, but that memory probably will be this segment. So the RDD which is created is a projected image of your original data in this memory space. So it will be local to this memory space. You cannot take this RDD and say, hey, work here. This is not possible. If you want to work on the data, the same data, you reload it into this memory, this Spark context memory, and that becomes another RDD local to this particular system. This is another RDD, this is another RDD. I mean, RDDs wise it is different, but ultimately it is the same data that we are actually loading here. Okay, so that is the point which we basically say that RDDs can't be shared between the Spark contexts. And these are additional, again, properties. We basically talk about immutability, fault tolerance. Here we use something called as DAGs. DAG is nothing but directed acyclic graph. It's like your data flow diagrams. DAGs are nothing but the flow of your process that you are defined. And it looks like a data flow diagram. Okay, so these are some of the benefits. You probably need to know certain things. You don't need to know certain things at this stage, but you need to understand that it is caching and it is a memory projection. So it is immutable. The RDDs are created in 3 different ways. It's read-only partitioned collection of records. This partitioning that we are talking about is logical partitioning. And it can be created in 3 different ways. You parallelize the existing collection. Existing collection means you have, let's say, a Python object, some object. Now you're basically moving that object, Python object, which is there in, let's say, a memory location only, but it is confined to a single node's memory, is now being moved into Spark's memory. That means it's a distributed memory. That's called as parallelizing the existing collection or existing object, you can say, collection of records. The other option is to directly load the data into Spark's memory. That becomes RDD by default. From an external source, we can do that. Or we can create RDDs by transforming or doing some operations on another set of RDDs, existing RDDs. Okay, and each of the RDD has a DAG in the backend, which explains how that RDD is actually created. This is called as lineage, data lineage diagrams. That's nothing but DAGs. So even in case if RDD has damaged partitions, that is your memory strip is probably lost. So the data can be recreated, the RDD can be recreated in the memory. So that is fault tolerance capability. And the only 2 things that we can control with Spark are, or Spark RDDs are, the persistence and partitioning. Persistence basically speaks about how long you want to have the RDD stored in the memory. Right? That's caching, basically, how long you want to keep the data there. Then we have partitioning, data partitioning. The RDD, which is there in the memory, can be further partitioned into logical splits, right? Logically, we are splitting the records. This will basically allow us to increase the parallelization while processing that particular data. If you have many processors which are free, then you can use those processors to partition this logical partition. Parallelly, you can get these things executed. Okay, that's your Spark RDD. Now coming to the last topic, which is Spark operations. As I said, there are 2 types of operations. Of course, there is third type also, but we'll not talk about that. Third type is nothing but one of these 2, which is dynamic, basically on what you're trying to do. The operations can either become lazy evaluation or eager operations. Transformations are lazy evaluated. And these give us RDD. Transformations basically help us to get the RDDs. And we will actually work with the raw data, which is there in the, let's say, disk. So RDDs are basically created here in the transformations. Then we have action operations. This is where the entire workflow that is defined, that's nothing but your application, for example, that entire workflow gets executed when you say action. And this is going to give us, it works with RDD and gives us the results, the final results. Okay, so that's your Spark operations. Two types, and these are some of the examples. Filter, map, group by, random, union, Cartesian, right? Reduce by key. These are all the operations that we have with respect to transformations, and these are some of the examples of action operations. Reduce, collect, first aggregate. Then we have the EDA calculations, minimum, max, standard deviation, variance. All these are your action operations, which immediately gives you the results. So these are the components, or these are the various important points with respect to Apache Spark from a theoretical perspective. Now let us try and install Apache Spark on your local instance. Now what should I do to have Spark working on my local machine? Oops, sorry, my bad. There are two different ways, of course, many ways where you'll do the hands-on with Spark. One is we can install it on local machine. This is a pseudo cluster setup. So your local machine is behaving like a cluster for Apache Spark. And this is what we are going to do now. We can have a Hadoop cluster, and then we can have Spark installed on this particular Hadoop cluster. This cluster can be created in cloud or on your virtual machines, your local machines or local servers. If you have multiple local machines which can be interconnected and created, then fine. Otherwise, you go with virtual machines. This is very simple. Cloud-based solutions, especially GCP. There is data proc service, right? And this data proc service is allowing us to do the Hadoop setup, Hadoop cluster setup, and by default, Spark also is getting installed into the cluster that we are going to create. So you can directly access that. If you are fine with this GCP account, then explore this. But let us now try and do local machine implementation. This can be OS independent. I am doing on Windows. Okay, let's try and do this. So let me pull up the document that is required for doing the setup. Yeah, this is my document. So three things that we need to have when you are trying to install Spark. Let me summarize this. The first one is Spark software itself. Okay, Apache Spark. This is an open source. You can simply download this from the website. I'll show you that also. It's a very small software. We will be able to do it in probably a minute or so. The second one is Java. For JVMs and for executing things in Spark, we need Java, and minimum is 8. Java JDK 8. This is minimum. Then the other one is a little tricky one. This is called as winutils file. Winutils.exe. This is for Windows specifically, we are trying to set it up in Windows, right? So this is going to be replicating your Hadoop binaries. These are nothing but your Hadoop binaries. So when you have WinUtils on your local machine, then this WinUtils is kind of fooling Spark, saying that, hey, this is a cluster, Hadoop cluster. So these are the three resources that we need. To get the Java installed, we need to go to Oracle website. But you want to check what Java version you already have, if you have. So to check that, you will search for Java. Here you can get configure Java. You can open this. And here you go to Java and search, view. You can see the version is 1.8. Right, update 301 in my machine. That is the update that I have. Okay, you might want to cross check that you have installed JDK 1.8 and then point it. You might want to add, if you have multiple Java locations, you might want to add it here. Okay. What if you don't have? So you can simply do Google. Okay, I'll open this. I'll simply say Java JDK 8 download. Java JDK 8. It redirects to Oracle website itself. Okay, you can see this is the main website, Java JDK oracle.com. You have to go to this. I'll go to the main downloads location. The latest one is Java 18, which basically you can see here. But if you scroll down, you see Java 8 also is given. You can click on that for Java 8, and if you scroll down, you have Windows version. Click on the Windows version, and we are using 64-bit option. So download this exe file. But for downloading, you need to have an account here in Oracle website. So if I say download, for JDK 8, if I say download, it will ask me to log in. I reviewed and accept this license, and we said download here. It will ask you to log in. If you don't have an account, you can create an account, and it is ready for you to download in a minute or so. Once the account is created, it's immediate access to your content. You'll get .exe file, double click it and ensure that it is installed. I already have installed, so I'm not doing this. But this is the latest update, 331. I have 301. JDK, remember you don't need JRE, you need JDK, development kit, not the runtime environment, okay? Once this JDK is installed in your system, you might want to set the location here by saying configure Java and go to the Java here, say view. You add this and give the path where it's getting installed. Remember the path when the installation is happening, and you have to set it here. This is not just one place. There is another location also where you have to set the Java path. The next one is Apache Spark download. And it can be done from spark.apache.org. You click here. This is the location where you can download your Spark. Directly download option is given. Libraries are there, documentations are there. Everything is provided here. You scroll down. This is the latest of the releases that you can see. Release notes and all those things. This is the download page, whereas this is the main home page for Spark. These are the key features. Batch and streaming data, SQL analytics can happen. We can do data science implementations here at scale. and machine learning can be done. And these are the various platforms that your Spark is known to manage. Python, this is the syntax. All you need to do is pip install Pyspark and then just say Pyspark. SQL, this is the syntax for SQL executions. This is something that we are going to do anyways. If you are familiar with Scala, then this is what you do. For Java, you're using the same Spark shell itself, which is based on Scala. And for R, we use Spark R library. This gives us a console, Spark console, where R console, where you'll be able to do the R implementations, right? R programming implementations. This is quick start. This is machine learning related examples. This is analytics and data science related examples. We can see a lot of other documentations also. Under this, you can basically talk about the documentation. But let us now try to download first. You can take any of these versions. These three are released. You can always go for the latest one, or at least one level next. N-1 version is always better. So if you select this, it will give you the link, right? Based on what version you're choosing, it automatically changes. You can download the latest one also. It's your choice. All these three are 3.x related services only, right? Versions only, so no problem. But if you have 2.x and 3.x, then probably there are certain features which are new in Spark 3. That's where you probably might see some difference. But otherwise, at this stage, any of these three options is fine. Now, in order to work with Spark, we need the Hadoop libraries. So pre-built libraries are there in this particular package. If you choose this, the first option, Hadoop 3.3 and later. So once you do this drop down and select the options, you will get the link. You can click on the link and it redirects you to this location where you are going to download this file. If you click on this, you get the file downloaded. I have an older version of the Spark installed. Let me take you guys to that. What is this? How come? Yeah, sorry, it is here. Spark 3. So my version, when I installed, was some time back. 3.12 bin Hadoop 3.2 version was there. Now you have Hadoop 3.3 libraries. Once you unzip this, you will get this folder. And within this folder, you have the software library. So download and extract this file, right? Spark file. Then comes the WinUtils. The WinUtils can be downloaded from either this link or this link. Any one is fine. I'm giving both the links. Just carefully look at the version. So I'll go to Hadoop WinUtils location. Here I have Hadoop 3.0. This is one link. If I click on the first link, then this is where I have Hadoop versions. The latest is Hadoop 3.2.2. You can take that latest one. If I go into the folder, I'll have winutils.exe. If I click on that, you'll get the download option. You download it. Okay. So Spark software, WinUtils software, winutils.exe file, and then Oracle software. JDK, Java JDK, which is downloaded from Oracle. These three are downloaded and made ready into your system. Then comes the installation. Of course, java.exe you will install. The Spark extraction is something which is required. And once it is extracted, we go into the folder called conf. In the Spark, we have a folder called conf, C-O-N-F. After extracting, you enter into this particular conf folder. There you will see sparks -defaults.conf.template. You're copying this template file like this. Make a copy. Remove the dot template and you can open this with Notepad. And here, this is one line that we add. Spark driver, you can see, Spark driver.host localhost. Right? This is one line that you add in the defaults conf file. In this file. Okay. Next, the file that you have downloaded, winutils.exe file that we have downloaded, it is a binary file. Okay, it's a Hadoop binary file supporting Hadoop binaries. Now it should always be placed in a bin folder. That's one requirement. So you can have the file placed under the Spark bin folder. You don't have to recreate a new folder. If you are fine, then use this location itself. If not, you can also create another folder. You can say Hadoop, and within that Hadoop, you can say bin. But folder name should be bin, and within that, you need to have your winutils file submitted. So place that winutils file that you download in this particular location, wherever you are placing your Spark software, under that bin folder. So winutils come inside the bin folder. That's all. These are the two things that we do. And next is we go to the environment variables setting. So you say in the starter button, you search for the environment variables. And here you see environment variables. Click on that. Now what you have to do here is set up three things. Hadoop _home in uppercase. This is a variable. And the value to it is pointing to the location where you have bin folder, right? One folder above. That is your Hadoop _home value. You can simply say new. Set up your name. So I'm just redoing this. Hadoop _home. And in the value, you can browse the directory. I'll say C drive, and within the C drive, I have a Spark 3, and this is the location. Simply keep that. When you say OK, you get this thing created. So Hadoop _home, then you have Java _home, and you also have to set Spark _home. If your Python is not set, you also have to set Python _home as well, and point this Python _home to the Anaconda installation. You might want to choose the Python, which is basically given by your Anaconda software itself. You can have multiple instances, but again, if you're pointing to some other location, then it creates confusion. So once this is done, once these libraries are done, setups are done, Hadoop home, Spark home will point to the same folder, then Java _home, and then we have Python _home. Once this is set up, once these variables are set up, you go into the path variable and open this. When you open it, you'll get these folders. Here we have Java JDK /bin folder mentioned. So again, you say new, point to that specific location. So whatever you have created, Java home, Hadoop home, Spark home, right, Python home. So you're going to point to the bin folders. This is JDK home /bin. This is your Hadoop /bin or Spark /bin. Then Python folder. We don't have bin. You can just put the binaries. I mean, Anaconda 3 has binaries also placed here itself. So you're going to put it here. Bin folder is not required for Python. So under the path variable, you set these things. That's all. Once this is done, you can open the command prompt and check. If you say Spark-shell, Spark is developed in Scala. Remember, it is developed in Scala, right? So Spark-shell is going to create an environment. That means it's initializing Spark context, and it is allowing Spark to work with Scala programming language. So look at this. It is creating the Spark context. By default is local star. And then it is using Scala programming language. So I will quit this. I think colon quit, if I'm not mistaken. Sorry. So you can say colon quit or Q. It will come out of your Scala shell. What we are basically trying to do is Pyspark. So as the name says, it initializes the Spark environment and brings up Python version, whatever the version that is installed. Okay. So this is the Spark context. Master is equals to local star. Next, you also have to set up this particular variable, Pyspark_Python. You define the name Python here. Give the name in small letters Python. If you do this, then you can also use Spider or Jupyter Notebook, either way, to work with your Pyspark. So either you can do it in command prompt, or you can use in Spider notebooks, Spider environment, or you can also deal with Jupyter notebooks. Right? Any interface is fine. Now, obviously, you'll not be interested to deal with a command prompt. At least I'm not interested. So I'll exit. All right, and we'll come to the Spark core commands. I will take that into Spider here. It's .py file, so we will be obviously running it in Spider. We can convert this by copy pasting into an IPython notebook and use this for same thing as Jupyter notebook also. I think I have that also. Let me check. Yeah, so this is the Spark code folder. Whatever the code you have seen in Jupyter Notebook is seen here in the Spider as well. The same code. Okay. So let us try and run this first. Whenever you want to start your Spark executions, we need to have Spark context created. Now, for creating a Spark context, we are initializing Spark session, right? So this is a Spark session, you can say. In order to work with Spark, we need to set up Spark session first, and then we will be able to interact with that particular session. To import, we use Pyspark.sql library. Pyspark.sql import Spark session. Then I'm defining the Spark session with an application name called Hello World app here. Here I'm saying Spark core exam. Builder is the module that we basically use. We initialize Spark session using that builder function. You can give the application name here, .app name, right? And we are saying get or create. This is to tell that we want to create an application if it does not exist. If it is existing, we are connecting to that particular application. Get or create. Right? So this is going to initialize or you're right, going to create your Spark session. And all this, I'm calling it as Spark. And this Spark, using this application, right, we are creating the Spark context. That's the first module that I'm doing. And the Spark context, I'm giving a name as SC. You can see here when I say SC, you get this UI. The UI is also available if I open this in a new window. This is your Spark, right, window. This is the UI for your Spark. This is the version, and the Spark context is this, and application name is this. We can also say Spark session of SC. You'll get this same thing. Okay. Then this is your code, friends. I mean, very simple code. You can see most of that is in Python scenario. Everything is Python. The first way to create a Python object is to deal with, right, creating it. So I'm creating a list here. This is in Spider. Same code in Jupyter Notebook. Okay, I'll execute it. I'm creating a list, and you can see the list is type. Let me remove the cells here. There's this. Yeah. So I'm creating a list. The data type here you can see is list. Now, to convert this Python object, a list object, into a Spark object, we use parallelize function. Now, this is going to create an RDD, and that RDD is called as R. I'm giving a name as R. You can give any name there. This is now going to sit in the Spark context related memory. And it is a, you can see Spark collection RDD at read this location. This is an RDD object. You can say Python RDD, parallel collection RDD. And when you say r.collect, this is like your print function. r.collect. In Python, we have print. The same function is right in Python called as, sorry, in Spark called as collect. Then we have r.glom.collect. This is to tell how many partitions are there for this list object. And you can see 1, 2, 3, 4, 5, 6, 7, 8 logical partitions are created. I don't want 8 partitions. I want only 3 partitions. We can do that by just saying comma 3. That's all. And this gives us 3 partitions. This is a way to create your RDD from an existing object, Python object. Now, if I have a file which is physically created, physically loaded into your file, your system, then directly we can push this data into an RDD. From here, we can create an RDD. So I will say SC is nothing but your Spark context. It's like pandas, right? So pandas.read VC. Same they say sc.text file. But Spark is developed to work on distributed environment. That is your Hadoop cluster. It's specifically designed to work on the cluster, right? The file is in this location. But what does Spark do? Whenever we want to work with Spark, it tries to access the HDFS by default. Because you are specifically saying the file is located in this single node, not on this location, you have to use this syntax, file : 3 slashes. File : ///. When you do this, you will be able to access a file which is located in your local file system. And I'll just execute this, and you will be able to see the RDD here. It says map RDD. It's a text file. And if you say .collect, that's when you will see the data. And RDD is an unstructured memory object. So whatever is the format in your file, that format is getting stored here. All right. So this is how we load the data into RDD. Okay. Now, if I have to show you another code, yeah. This code is basically allowing us to store the data in a structured format. So what we are doing here is we are trying to create a data frame. We have RDD. We have seen how RDD is created using sc.textfile command. But how about creating a data frame? So CSV file, when we load, it gives you RDD, but now I want to try and create a structured object. A data frame can be looked at in Spark. Okay, in Spark, a data frame can be seen as a schema RDD. Schema RDD. All right. So let us see how we can do that using Spark capabilities. So this is the same command. I'm not re-executing it. Okay, and I also want to show one more thing here, the UI. These are the jobs that we have. Different jobs are created. 4 jobs are completed till now. And when I click on the latest job, you can see the DAG. DAG is nothing but a graph which allows us to understand how the RDD is created. It's a text file that is being read. So from this point to this point. When I click on that, you can see the location also. All right. So this is the information that you can access from your Spark UI, which is by default running on the port 4040. And this UI is available only till your Spark context is active. If you close your Spark context, once your task is done, it's good practice that you can release the right resources that are created for Spark context. So you say sc.stop, stop the Spark context. When you do that, all the resources are getting released back into the main pool of resources. So in that case, you'll not have this UI. It doesn't work. It will be active only until your Spark context is available. Remember this point. So let us now create a data frame or schema RDD by using the Spark read.csv function. Pyspark.sql data frame reader.read.csv. This is used to read the files directly. You can also say text file, sc.text file, as I've just executed. Right? So first, I'm defining the location of a file. I'm using any file, random file. In this example, I'm taking a larger data set. This is also something that is readily available. You can Google for this data. It's available in various platforms like Kaggle, Data World, and various other forums also. I'm taking 100,000 ratings for 9,000 movies, and these ratings are given by 600 users. So ratings.csv, this is placed in a specific location in my C drive. I'm pointing that with a variable called data and simply say read.csv, spark.read.csv, where Spark is the session that we have constructed here. You can see Spark, right? Spark object. You can also say Spark here. Let me say what happens when we say Spark. Right? Your Spark session, that is nothing but your Spark. So I'm going to use this particular session to load the data in a data frame format. When I do this, the data is getting loaded. What happened? Cannot call within context. Why? Currently active Spark context was created. Oh, okay. Okay. Spark context is already active. It says it doesn't work here. So what I'll do is I'll try and stop the Spark. I'll recreate this. Okay. So you can see here, this will not work anymore. Why is it working? Where did I take this UI from? I think here, right? Say sc.stop. Okay. It should not work now. Yeah, it's not working. So my Spark context is ended in that previous other session. Here I'm creating Spark context again. I don't have sc, right? I'm just saying Spark. So this is spark.read.data frame. So now accessing this data, either you do this or that, both are same, guys. I'm just recreating Spark context here by a separate name, which I have not done here. Okay. I'm directly using Spark, this Spark application. Read.csv, the data. Now, when I say df.show, you can see the data here, but this data is actually having a different column names altogether because the file is read as is, right? We are not passing any arguments. There are other arguments that we can pass. The print schema function is very, very interesting function, which infers the schema of the data by looking at the contents, just like your dynamic loading. So when you say print schema, you can see everything is string. This is because the first entry into that data is the column names. So when you just pass the data as is, without passing the arguments, Spark reads the entire data as its content, table content itself. It does not differentiate between the titles and the data. Okay, that is the reason why, because it is string data, every column is set as string itself. Now, what if we can pass additional arguments like this? So here I'll say path is equals to data. Then this data has delimiter as separator. Then I'll say header is equals to true. If you have any code, you might want to put that code here. Then encoding is by default UTF-8. And then you can also say infer schema. So we are passing all these different arguments. When I do this, right, when we do this, you can see the df show gives me these details. User ID, movie ID, it is now able to understand that header is also there. The first row is always considered as header when you say header equal to true. Now let us also look at what is the schema. So you're specifically saying that, hey Spark, dynamically load the data and understand what is the schema. So if I say print schema, you can see it says integer, integer, double, and integer. Double is nothing but float. Right? We can also ensure that we give the schema that you want. So here you can see we are passing the schema. I'm saying integer, integer, double, integer. You don't need to pass infer schema equal to true because this is going to do the automatic dynamic identification of schemas. But if you want to specifically give a schema, you can do that. And if I say show, this is the data set. Print schema is basically giving us this. Then the next command, describe command. So let us reload this. And I will load these files. Describe is going to show us the data. This is the same describe function that we have in Python. If you see, we generally say describe, right? Data.describe, it gives us these 5 pointers. That's the same thing that it is giving: minimum, maximum, mean and standard deviation, and total count. Of course, it doesn't give us that median calculation, first quartile and third quartile calculation here. And if you say explain, it basically gives us all these right, the details like what is the format, what is the memory file, right? All those things it tries to explain. The user IDs, how many IDs are there, unique IDs, right? All these details are given. Okay. And once it is done, of course, we will have to stop the session. I'm saying spark.stop because I've not defined anything as SC in this case. SC was defined here. Okay. So this is about your loading of a file in a CSV format. We can do a lot of manipulations here. Okay. I'm not running through this, but yeah, if you want, you can probably do all this, right? Experimentations. I have two different data sets, ratings.csv and movies.csv. I'm trying to load both of them and then do the manipulations. In movies, show 15, print schema, then right, movies where condition is applied, SQL conditions. Movie genre, from movies, you just print this. So everything basically you can see is on the movies data set. Okay, I'm not running this. I'm going to now talk about clustering application in Spark. Okay, this is Let's see if I have this available here. Yeah, clustering is there. I'll open this k-means clustering code here. You can see everything is like a single script because I'm opening this in Python file. Right? You can also convert this into a IPython notebook. I'm going to only execute this in Spider. I'll just show you what exactly is happening here. So I'm importing the Spark session and I'm defining my Spark object application. And for implementing clustering in Pyspark.ml, this is ML library, I'm going to import k-means module from the clustering module. I will say data is equals to university's data set. And then I'm trying to read the data set into a data frame. You can infer the schemas and all that. Now, post that, whenever we want to work with machine learning library in Spark, the fields have to be converted into a vector form, a single vector. And that vector creation is being done here. Then we are doing standardization. And then here we are doing k-means. Right? And you can see the output here, k-means output. So let us run through that. I'll run here now, line by line. I'll try to execute. Yeah. So Spark session, this is Spark application I'm creating. Because it is like the notepad now you're seeing, you'll be able to see the messages. Here I'm importing the library called k-means, defining the data location, reading the data, university. This is SQL data frame. This is Spark's data frame. When you say show, it gives you the table representation. When you say print schema, it gives you the schema interpretation. We have said infer schema is equals to true, right? So it is automatically inferring the schema as well. Then here, as you see, we need to create vectors, right? All the fields that we have needs to be converted into a vector form. To do that, I have this feature engineering library called vector assembler from Spark ML. I'm defining what features you might want to convert into a vector, except for university name, which is a string. I'm taking the remaining numeric values into the list. This is a list of 6 columns. And I'm passing this as input columns for your vector assembler. The input columns are the 6 columns, separate columns. And vector assembler is going to create a vector and give the output, which I'm labeling as features. This is default syntax. Output columns is features as something which by default we use. When I run this, you get a vector. Oh, sorry. Let me run this. So you get feature vector, which is a, again, Spark ML feature. Right? If I try to open it, obviously you'll not be able to read this. Oh, why is this error coming? Okay, not sure why that error came. We'll try and check. Now, this feature vector is used to transform the university data set into a new data field here. And this is your SQL data. When I say show, you can see the original data and this features is a vector. Let's see if I can open this. No, I cannot open it here. right? So this is your data object. 13, 30, 10, 89, 22, 13, that is what you're getting. So each row, which has multiple columns, is converted into a single column as a vector. This is a mandatory step for your machine learning libraries in Spark. Now I don't need all the columns. I need only the 2 columns. So I'm doing select command. So from this, you can either say data dot select, or you just do this. Either way it works. And this becomes my final data. And if I say show, you can see it is only taking university name and the features. Now, once I have the data, on this data, I'll have to apply standard scalar function. This is to ensure that we do standardization. Standardization is nothing but x minus mu by sigma. The input column for standard scalar function is features column, and this will get transformed into z features, a new column called z features. And we are using standard deviation. True, mean is equals to false. That means mean should become 0, standard deviation becomes 1. Standard scale. This is the same function that we used in Python. So I have to import it first and then use it. So I'll get scalar data. Now using the scalar data, this module, I'm trying to convert my final data and storing it into the scalar model. And I'll say transform the final data into this. I'll get cluster input data. Now, if I say show, you will see that this data is standardized, 13, 10, right? All these values are standardized here. All right, different calculations, multiple decimals and all those things are coming up. Now, once this data is standardized, we use this data for simply doing k-means. I want to work on z features. K equal to 3 is the number of clusters that you are trying to pass. K-means, right? This is something that you can see. K-means clustering with k-means plus plus, like initialization mode. And this is from Pyspark. Okay, this is not Spark k-means. This is this is not Python's k-means. This is Pyspark's k-means. And k is basically the number of clusters that we pass. Okay, that is given here, the documentation. We can pass and get the k-means done. Now we are trying to use this k-means for your clustered, your input data, which is specifically created for doing the clustering after standardization. So I get model. I'm calling it as model K3 because I'm using k equal to 3, right? So k means 3, and when I apply, I get model 3. I'm also doing the predictions here, clustering. These are your cluster centers. Six values are there. These are your cluster centers. For 3 different clusters, I have 3 different centers. I'm just printing those things here. So this is a simple demonstration on how clustering can be done using Pyspark. Now, you might want to basically get hands-on with this code, isn't it? I definitely know that you all want this Pyspark code. Now, I would suggest you people create your own code by referring to the documentation in the Pyspark, in the Spark UI itself. I'll go to Spark here. This is the location where you have Spark, right? This is the Spark home. You'll go to the documentation. You can say latest releases, or you can also go to the lower versions also. And these are some of the examples. Launching on a cluster. How do you start on Hadoop? How do you start on right, your Apache Mesos? This is deprecated. No more we are using this. And this is programming guides. So you have programming guides here. This is quick start. The very basics are given. You can just click on Python, interactive analysis with Spark shell, Pyspark, or you can say Pyspark, and you'll be able to do this manipulations. On data sets, this is how you can do the analysis. Some basic hands-on is given here. Now, if you go to the machine learning module here, this is more important for us. If I go to MLlib, you can see there are two different options. One is RDD based library, which is actually called as MLlib. We still use this terminology, but this is in maintenance mode, and in future versions, this will not be there. It will be completely removed, deprecated. What we are basically doing is Spark ML module, or Spark MLlib, you can say. Spark machine learning. As of Spark 2.0 in Spark MLlib is in maintenance mode. We might want to use data frame based API, which is called as Spark ML package. That's nothing but this main guide. So if you start here, basically understand what has changed and all that. Now, if you want to do the coding, you come here. This is Spark ML library. And there are various examples that are given here in different languages. There are some concepts which are not defined in R programming, but for Python and Scala, almost all the examples are given. These are with different data sources, image data, libsvm data. So how do you access those image data in Spark is also given here. Right, this is libsvm. This is like your regular data. Okay. Then we have pipelines, ML pipelines, right? And you can try and read all this content. We have, yes, these additional values. We did standard scalar in our clustering code, right? So I'll just open that clustering code. Standard scalar. Standard scalar transforms a data set of vector rows, normalizing each feature to have unit standard deviation and zero mean. Example is given here, and this code is also given. We've also done, if you remember, I have also done vectorization, right? What is that? Vector transformer, vector assembler. That is this vector assembler. Yeah, this is your vector assembler. Vector assembler is a transformer that combines a given list of columns into a single vector column. These are required. So on and so forth, different right libraries are given here for doing feature engineering and all that. Okay, so you can just read about them. Then classification and regression. You have logistic regression, you have binomial, multinomial, decision tree classifiers, then regressors, ensemble techniques. Then we have clustering. K-means clustering is given, LDA is given, Gaussian mixture models are given. Collaborative filtering is nothing but recommendation engine. Right? Recommendation.als is used here. Then we have frequent pattern mining. They're more like your association. Frequent pattern mining is more like an association. Yeah, you can say association rule learning. There are advanced topics. So a lot of readily available code is given for you. You might want to take any random data set, use the code examples that are given, and try to enhance your applications to apply to that particular data set. All right. So this is about your Spark using Python interface. We initialize this application by calling Pyspark. So this is Pyspark as part of your masterclass, and hope you have learned something new, friends. Tomorrow, again, we will be connecting to discuss about data engineering and ML ops related concepts. I'll also talk about the difference between various data sources and data pipeline generations and architectures and all that. So tomorrow, again, we will be connecting to discuss about something very interesting in the world of data science. Until then, take care of yourself, stay safe, good evening, and good night, friends. Thank you.